So this is our large-scale immersive visualization system. It is a VIzBox C4. It has 3 walls and a floor for a total 4-screen system. Rear projected, active stereo. We're using these type of shutter glasses that are RF linked to the system, and all 4 displays are synchronized together through the one computer that's driving it. We're using a AR tracker optical tracking system. So we've got these glasses with these reflective balls on it, and a series of infrared cameras around the perimeter of the arena are looking for the arrangement of these rigid balls in this structure. And by doing that, it can tell where the user's head is and its orientation within this space. All 4 screens are being rendered from that point of view. So to the user, he sees a seamless spherical environment while the system's in operation. So as I walk into the system, it starts tracking my position. As I move around, all 4 displays shift to accommodate my new head position. To external viewers, there's going to be a good degree of parallax, but to the person that's wearing these control glasses, they see everything in a seamless environment that always looks good. What we're looking at here, this is a model of cranial arteries taken from an actual MRI. It's left over from another project where we modeled up a stent that goes into this, which is a cranial aneurysm, and then we do a fluid flow analysis of the blood through the aneurysm, both before and after the stent is put there. We developed the model by segmenting out the arterial matter from MRI data, which the MRI data has a bunch of different densities in it. So we looked for all of the areas that had this specific density that equated to vascular tissue. So we worked with students and faculty from mechanical engineering, and we provided the segmented model of the arteries. Mechanical engineering students and faculty actually worked on the fluid dynamics of the project. This is a model of a brewery that was going to be built here in town. It's based off of the architect's actual working drawings. So the architect that we were working with did all the models, did all the textures, created this entire environment, and then we went through the exercise of taking his working drawings, which was done in a piece of software called Revit, and converted it over into this environment. A lot of the applications that we developed for this system are written in the Unity game engine, and we use another piece of software called Gill for Unity to handle distributing the scene across all four displays here. The reason we like Unity is because it allows us to target multiple different environments and applications. So we can develop for a cave type system like this, or we can develop for mobile devices, desktop, we can develop for the web, Linux, Macs, whatever we wanted to do. This application also was a proof of concept for other student work that we have here. There are students in the ETS department, Environmental Technology Services, that they study this Revit application, so we can take student projects and allow them to see their work from the inside out, to scale, fully textured in this entire environment. This project was based off of a open source piece of software called the Worldwide Telescope that reads in data from a variety of different star catalogs and projects it into a 3D space. We've got 60,000 neighbor stars, 9,000 bright stars, 90 constellations, 9 planets, 14 moons, all located in 3D space based off of the Julian date. As the Julian date progresses, the simulation progresses. So we see the Earth spinning around, the moon is spinning around us, And then if we turn towards the inside of the solar system, we can see the other planets marked by the trails that they leave behind. We've got Venus, Mercury, the green one over there is Mars, and then we can go to different planets and see what the solar system looks like from a different point of view. So now we're out here by Mars, and we see Mars spinning around here, and we see the other planets in the solar system as they rotate around the sun. This was developed by a team of software engineering students who did the work of reverse engineering a worldwide telescope and converting it into this environment. And then they worked with the VIzLab to actually create this display. And we've got different versions of this. So this runs on a mobile device. It also runs in here. We've done a version of it for the web. So another collaborator that we work with quite frequently is Dr. Bill Gorsica in the art department, and he's teaching courses in the Unity game engine. And this was student work from one of his digital art, game design and modeling courses. So each one of the students had to envision a geometric piece of fruit or food. So we've got things like strawberries, pineapple,